Well, thank you very much for this kind introduction. Good morning, Vienna. Good morning. So this talk is about intelligent machines, and the reason why you have the Rodin on the left and the less human guy on the right is that this is all about comparing the intelligent machines that are biological, i.e. machines that were evolved through 3.5 billion years of evolution on Earth, with those that are designed. And what I will talk about is on the left-hand side, we'll talk about all the biological aspects of machines like neurons, the brains, the ears, the eyes, the legs, how we learn in schools, of course, as humans, and then how important these disruptions are that come about with new technologies. And I will concentrate on the car industry in particular, because we've seen so many disruptions in the computer industry. I give another talk called The 6 Waves of Computing. And I have concluded that what is happening in computing, that at the end of a wave, when you normally have a few companies that completely dominate the wave, they always miss the next wave. And I think a similar thing is going to happen in the car industry. And on the right-hand side, we'll compare these components on the left with the artificial components on the right. So we'll compare the neurons with the transistors, and so on, until we come to the human goals at the end. And if there is one message that I want you to take away from this talk, it's this point about human goals. That this is not about software actually at the end. Of course, software eats the world at the moment. Software is the most important tool that we've developed over generations of clever people who are trying to improve our lives. AI in particular and machine learning is the most powerful tool that humans have ever developed. But that is actually not what it's all about. We need to decide, especially over the next decade or two, what our goals are, what our values are, and agree on it. And this is the hardest thing, and I will show you how hard it is and how bad we've been there in the past with these goals. So let's start off with the neurons versus the transistors. First of all, the size. Neurons are huge. They're 20 microns compared with 20 nanometers. So they're 1,000 times bigger. So the transistors have it. They win that race. The neurons are slow. They're typically a kilohertz. So I will show you the neuron spikes in a moment, these spikes, because neurons in a funny way are digital. You know, they send out these spikes, and they're always the same height. They're about 64 millivolts, and they're always the same width. They're about a millisecond wide. Computers run at gigahertz, so 1,000,000 times faster than our neurons. Interestingly, our brains have about 100 billion of them. And the biggest memory that we have in a single chip right now is actually about 10 billion. So the neurons have it there. The neurons are actually, the brain is 10 times denser than the transistors. But when it comes to connections, and that's the last secret of intelligence, really. Intelligence, for me, is knowing what to do next, and I will come back to that. It's an unusual definition when I first came across it, but knowing what to do next for a goal seems to be a very nice definition of intelligence. And the secret why our brains are still faster in knowing what to do next is actually the connectivity. A neuron typically has 1,000 to 10,000 connections. So those of you with a bit of a mathematical bent, which I hope most of you have, you will soon realize that when you have spaces of 1,000 to 10,000 dimensions, so these very high-dimensional spaces are incredibly dense. So if you want to find anything in the brain, with one hop, you're connecting to 10,000 other neurons with 2 hops. You've got 10 to the 4 squared, so that's 10 to the 8, that's 100 million connections. So you see that with a very small number of hops, you get to all the interesting things in the brain. Now let's look at what this neuron is like. Well, a neuron is unbelievably complex. You know, it's a cell, so because it has to live, it has to have all the paraphernalia of a cell, so you know, the DNA in the middle and the mitochondria that produce the energy, etc., etc. It then has these long axons to connect to the 10,000 other cells through these synapses, and it has these dendrites that again fan out to collect signals from 10,000 other neurons. And then, just to make things more difficult, some of the neurons actually go from the back of our head to our toe, so they're actually 1 meter long, or 2 meters long, and in order for the signal to get there quickly, we also have designed these myelin sheaths so that signals travel faster because they have a nice electrical environment. Since I live in Cambridge and you know, I did my PhD there, I'm always keen to tell people that interesting things happened in Cambridge. And one of the interesting things happened that Huxley got his Nobel Prize to work out why it is that these neurons work. And here is the formula that underlies neural activity. It's basically a summation. So the function looks like this. You have a threshold function. So it sums all the 10,000 inputs that go into the neuron cell, and then if the inputs exceed a certain threshold, bang, it goes and produces one of these spikes. And as you see, these spikes, unlike sort of computer wave functions, they're quite irregular. And often the signal strength is just the density of these spikes. So if lots of spikes appear, then it's important, and if spikes don't appear very often, then it's not such an important signal. So look at a transistor. A transistor is incredibly simple compared with a neuron. It actually only has 3 components. There is the source, where the electrons come from. Then there is a gate that determines whether the electrons get through to the drain or not. And then there's a drain that if the gate is open, the electrons go through here and get drained out, and that's it. So that's why they're so much smaller, and that's why they can be so much faster. Now comes the crucial point of my talk, and that is, look at the function that we put together with these NAND gates. So this is a NAND gate, you know, and this is the truth table for the NAND gate. So if this is false and this is false, then the output is true. And the only way you get a false output is if both of them are true, then the output is false. So it's this binary system. And of course, all of you know that computers work on a binary system, on a 0 and a 1. And in a way, and this works incredibly well, you know, and we've got big numbers and big computers, and we can calculate them very well. But it had the slightly unfortunate aspect that people associated the zeros and ones with falsehood or truth. So there is a sort of seductive suggestion that a 0 is false and a 1 is true. And then you say, well, how do you deal with analog signals? You know, this is a digital signal. Well, if you have lots of bits, you can then approximate an analog signal, and it sort of works. So now let's put these components together into a whole brain or a whole computer and compare that at the brain level. And what do we find? And this was a real surprise when I did the research. That the total capacity of a brain, because of this component here that I found, which really surprised me, it's a package that is 1 gram and has 512 gigabytes in it. So it's half a terabyte in a single package. And because of it's a gram and the brain is about a kilogram, you can pack more semiconductor bits into a kilogram than in our brain. Now, it's difficult to know exactly how big the memory of our brain is, but the best estimates from our biological friends is between 10 and 100 terabytes. But a kilogram of these chips, these packages that I talked about, is actually 500 terabytes. So the artificial computer actually now has more memory than our own memory, which surprised me. The next point also surprised me, that the processing power that people estimate our brain has is between 10 petaflops and an exaflop. And the best GPU that we have at the moment, which is the most processing power you can buy in a package, is about 10 teraflops. So the brain, in absolute terms, is actually still 1,000 times more powerful than the most powerful single unit that we have. And that's the important thing, single unit. The point about single computer units is that you can connect them, of course, and have many of them, and we've got these data centers and the World Wide Web that in its aggregate, of course, is much more powerful than the brain. However, the no-context aspect of the brain is its power consumption. We do all that with 20 watts. So if we were to build a computer that had the equivalent of our brain power, it would consume 200 kilowatts. So this is more than this whole room, this whole building consumes probably half the city. So it's 10,000 times more efficient than our computers at the moment. As I hinted already, the secret to the power and the performance of our brain is its connectivity, the fact that we can do lots of things in parallel. So these are massively parallel computers, and this is a sort of picture of a brain. This, interestingly, is the output of a piece of software that runs machine learning on our graph core processor. I never thought that I'd do another processor. The ARM has been quite successful. We sold 20 billion of them last year. But this new processor called the Colossus is actually not one processor. It's 7,000 processors in one. And this is another project that I'm supporting at Manchester University, where we use 1 million arms, 18 arms on a single chip, to simulate 1 billion neurons in real time at the spiking level. That's why it's called Spinnaker. And this is a picture of the human connectome. So if you take an fMRI, an MRI picture, which was taken by a company, a university to the west of Cambridge, which is a perfectly reasonable university, and it shows 200 different brain regions from 416 people, and it really looks a bit like this, a bit like the software picture of what this machine learning processor does. We call it the IPU, the Intelligent Processing Unit, and it's only the 3rd time in the history of computing that we've needed a new piece of hardware, a new type of processor. The first time was this historic shift from complex instruction set computers like the Intel processor to reduced instruction set computers, the ARM, that I'll talk about a little more later on. The second time, we realized that if you want to do very good graphics in the world, and you've seen lots of video screens and also virtual reality screens out there in the foyer, they are all run by GPUs, by graphical processing units. Both of these units have an intrinsic problem, that at 3 gigahertz, the speeds are so fast that even the small distances on a chip run up against the speed of light. And this is not something that we're going to change anytime soon. So we cannot run chips faster than 3, maybe 5 gigahertz. So you can't make a single processor any faster than they go right now, and we've topped out at about 3 gigahertz. All these Pentiums that you buy in the PCs, which are the top end, of the range, or the top-end ARMs now in the big smartphones. They all run in the gigahertz region. So the only way of getting more processing out of a computer is by parallelizing the problem. And as you as clever software people very well know, and I'm sure lots of you working on parallelization problems, there is no generic solution to the parallelization problem. In fact, it can be shown that it's impossible to have that because problems are so varied. As luck will have it, many machine learning problems, because they work on very large databases, have a natural way of being parallelized. So using 7,000 processors on a single chip with 350 megabytes of RAM, all on a chip, when it's just taped out, so it will be the biggest chip in the world. It will have about 3 centimeters on the side. So this thing is a colossus. And the secret behind the phenomenal performance increase over a GPU with the IPU is that it separates the calculation from the communication. So, as you know, in a normal processor, you mix up the communication part and the calculation part. So when you want to communicate, typically an interrupt comes in, and interrupts are really bad news. Because when an interrupt comes in, you've got to, save the registers, load in the interrupt routine, execute the interrupt routine. When you're finished with it, then flush the register again, pull the old registers in, and by the time you're done, you've wasted an enormous amount of time. You cannot do this fast. And if there are lots of interrupts coming in, you're really screwed. The secret to the success of the intelligent processing unit is a new protocol called the bulk synchronization protocol, where you separate the calculations from the communications. So what you do is you have these 7,000 processors that work on their typically 50 codelets each, so you've got to balance them quite well. You wait until the last one is finished. So it's totally asynchronous. They don't talk to each other at all during that period. But they get on with the job. They calculate flat out. When the last one is finished, then there is a non-blocking network. About 30% of the chip is just the network, so that everybody can talk to everybody else at the same time. So that's the communication phase. No interrupts. This is just everybody talks. At the end of the talking, everybody calculates again. And this different architecture gives you a factor of 10 to 100 times more performance than the GPUs at the moment. So it's a very exciting development. So let's go to the ears, the beamforming microphones. All of you know about the Amazon Echo, the Google Home, etc. Why is this now possible when it hasn't been possible before? One is voice recognition. Voice recognition now is better than human. I've been working on voice recognition for many years. I've supported many companies and sold a number of companies. The last one was called Vocal IQ to Apple. That's why Apple is now in Cambridge. But the secret why we can now do it across the room is the secret that we mastered through evolution, which is our 2 ears. With our 2 ears, when you listen to me, for example, you know where the sound is coming from, and your brain automatically cuts out the coughs and the noises that go on elsewhere, because you know that's not me, that's coming from elsewhere. So you can noise cancel out everything, and you do this, of course, unconsciously. Now we've figured out how to do this with microphones. So an Alexa has 7 microphones at the top. It quickly, you often, I'm sure you've noticed that there are LEDs at the top, and the LEDs will whiz around and then stop in the direction of the voice. And that allows you to do voice recognition across the room. Now, how do we see? We see with our eyes, of course. And these artificial ones see with their cameras. And you will not be surprised then when we compare the eyes with the camera, boy, do we lose. We lose on the resolution. These microscopes are 1,000,000 times better. But the most impressive difference, and I didn't realize this until recently, is the fact that cameras have become incredibly fast. like 10 to the 10 times fast. So there are now picosecond cameras that have picosecond resolution. And because light travels a foot a nanosecond, so in a nanosecond, light travels this fast. In a picosecond is a thousandth of a nanosecond, it travels this fast. So there's this movie that they've done at MIT where there is a scene with, I don't know, an apple and a little toy car or something. And they have light sources that switch on very abruptly. So you've got this light wave coming from the left. And the camera sees as the light travels across the stage. It's amazing. So we're very good at that. And of course, the frequency. But in my opinion, the most important difference is none of this. The most important difference is that we have two eyes, and if you look at the World Wide Web, well, there's at least 100,000 cameras that everybody has access to. So it's the number of cameras that makes the difference, and that's one of the important reasons why I'd much rather trust a machine than a human when it comes to driving a car. Humans are not very good drivers. And the reason is we don't have eyes in the back of our heads. We don't have radar. We don't have LiDAR. So the amount of information that we have, although we're clever chaps, right, the amount of information that we have is a tiny amount compared with the amount of information that we need to process in the car. By the way, the processors that we put in the cars, I've got an investment in a company called 5AI that hopes to be the first robotaxi company in London. We guess that we need 250 teraflops to run the bloody car. This is the biggest, this is 10, I'm very proud of these processors in there. This is 10,000 times the processing power in the fastest smartphones at the moment. So there's a lot of processing power in there. And there are early examples of that, of course. Let me just show you one of them. This is a Tesla car, which is actually not state-of-the-art anymore, but it gives you a feeling for how this thing looks to the computer. So this is a car. As you will see here, he's not touching the steering wheel. He's coming out of the parking lot here, and this is what the cameras see. So this is the left rear camera, this is the front camera, this is the rear right camera. These boxes, the green boxes, are the cars in front of him that he's not worried about. The blue boxes are the ones that he might crash into, so they're dangerous ones. And then as you drive down, you'll see he'll come across another one that he doesn't mind because it's in the same, he's driving the same speed as he is. And then we'll come on to a traffic light in a moment. And that's getting tricky because traffic lights are much smaller than cars. And here we go. And then he turns left. Here's a traffic light. You can see that it recognizes the traffic light. Of course, it stops in front of it. Again, traffic light. So the problem is one of classification of objects. And like with voice recognition, deep learning basically solved that problem. Deep learning is just a most spectacular success, and in a way an unexpected success, because people like myself, I almost changed my PhD from physics to AI a few years ago, because I believed passionately in AI, and I believed that autumn, so 6 months away, we're going to have a world chess champion that's a program. Now, it took another 20 years for that to happen, so we were a little bit optimistic. But the basic ideas of deep learning, which was all these basic algorithms that now work so well, existed then. So why did the basic ideas, why did it not work? Jeff Hinton, who is one of the gurus in AI and one of the fathers of deep learning, now at Toronto, I got him to give the keynote speech at the Royal Society meeting that I organized for machine learning. I'm the only venture capitalist who is also a fellow of the Royal Society. I'm more proud of that than my knighthood. So I'm keen on this academic stuff. And Jeff gave 3 reasons for why machine learning works now and didn't work in the past, in ascending order of importance. The first is we've got more processing power now than there, now considerably more, and he said that was very welcome. The second was further improvements in algorithms. Now these algorithms, there are clever chaps like you out there who find ways of speeding things up considerably by being smart about how you program. But the third one was the killer. The third one is really the thing that makes it work, which was the availability of large, high-quality data sets. So large, high-quality data sets is really the secret of self-driving cars and recognizing these objects, combined with all these sensors. So you see there's adaptive cruise control, long-range radar, there's emergency braking, pedestrian detection with LiDAR, then there are cameras, then there are park assist with ultrasonics, and you see it surrounds the whole car. So it looks sideways and backwards and everything. And I don't need to explain convolutional neural networks to you. That's what you all know and what you're here for. Now, the second thing that I wanted to show you is that if you design something from scratch, rather than having evolution do it for you, you come up with surprising interpretations of a leg, like this one from Boston Dynamics. So Boston Dynamics is a really interesting company that produces robots, actually not using machine learning, but using just traditional control techniques. And this is what they did with a leg. They gave it, they didn't put feet at the bottom of it, they put wheels at the bottom of it. And I was really impressed when I saw this video for the first time, what they managed to do with just with control circuitry and the wheels on the end of legs. Of course, it has no problem doing this like this. It's very hard if you do it as a human. And it can do pirouettes. But we'll soon see it can do that. But it can do that, which is really quite interesting. So this is quite hard to do. So you have an endpoint in 3D space, and you let this guy do squats and keep that point fixed, and he can do that. And a human wouldn't pick up a crate like that, right? So you've got new ways of designing things so that this is actually quite a sensible way of moving around the crate. Now, I didn't normally think of that. And it can do that, which is surprising. Now, watch it coming down. It slips. You'll see in a moment. Here it slips, you see, but it doesn't fall over. So the control circuitry there is really most impressive. And yeah, it can do that too. And it also has emotions, as you will see, because it can jump for joy. So here you see that we've got this great design freedom So then the question is, what is machine learning? After I organized this first seminar on machine learning at the Royal Society a few years ago, we decided that machine learning was such an important development, as I said, arguably the most powerful tool that humans have ever developed, that it's worth defining what machine learning is. So, since the Royal Society is a very learned society, it sort of goes and thinks about this very deeply, and what we came up with, I did this with Demis Hassabis of DeepMind, and we decided that systems that learn from data rather than following pre-programmed rules was a good way of defining machine learning. And then one of the definitions of intelligence, and I wished I'd thought it up myself, but I gleaned it from the roboticists, is knowing what to do next for a goal. These are all different branches of machine learning, as you probably know. start off with supervised learning, where you have a labeled data set, like with face recognition, you say, this is Johnny, this is Mary, this is Johnny, this is Mary, this is neither of them. And then you've got a labeled data set, and you can easily do the machine learning on that. Unsupervised is a little harder, because you don't have labels, so you get all these faces, and you've got to decide whether these faces are similar enough that it's the same person, but you don't know, because you don't have labels. Reinforcement learning, you are given a utility function, a score, like in winning a game. That's what DeepMind did very well with the Atari games. So you have a reward function. And the hardest, this is increasing the degree of difficulty. And then inverse reinforcement learning is really the hardest, where you don't know the reward function. And you basically have to work out yourself what a good thing is, what a good reward function is, by watching humans, as it were, with the cars. And we are not good people to watch because we don't drive very good, but this is the best we have. Speech recognition, as I said, is better than human now, and so is object recognition, and these recommender systems work quite well. If there is one slide I want you to remember from this talk, it's this one, because it's such a fundamental shift in the way we think. It's this point about zeros and ones that give you this seductive suggestion that a 0 stands for it's false and a 1 stands for it's true. And as it turns out, describing the world in terms of a first-order predicate calculus, which is basically what this is, that things, it's raining or it's not raining, it's red or it's not red, or it's, somebody's a good guy or he's not. Somebody's a good guy or he's Trump. So, but as it turns out, these truths are only available in mathematics. The minute you hit the real world, nothing is ever true, nothing is ever false. Things are just more or less probable. Now, in most cases, of course, it doesn't really matter. If it's very, very probable, you might as well say it's true. But the subtle change to seeing everything as probabilities causes very fundamental changes in our basic thinking. One is you've got to give up on determinism. Things are no longer determined. You cannot prove to anybody ever again, and people just have got to get comfortable with that when a car is driven by an AI and it crashes, this will happen. You cannot prove that this car will never crash again. The only thing that you can do, and there's this big discussion going on, what improvement over human driving is necessary to let these artificial cars drive, these autonomous cars drive. Is it 100 times? Does it have to be 1,000 times better than humans? But you can never say it will never crash or it will never kill anybody else. And you've got to get comfortable with that. That's just the way the world is. So everything is becoming statistical. But what you gain is you don't have to program everything. Of course, don't worry, your jobs are fine. As long as I can see, so programming will be very important. But in addition to programming, you now have teaching. You can teach computers by just serving them up the right data sets and letting them conclude patterns from that. But it needs very big data. So this is really a secret. And here we come to the conclusion, the most important conclusion of my talk, which is all this needs human goals. We need to decide what goals to give these AIs before they start doing their own, and that is the genie problem. We are not very good at wishing for the right thing. In fact, we're crap at it. Whenever we think we really want something and it would be good for us, it turns out later on that it's not good for us. We wished the wrong thing. A little bit about artificial intelligence. Steve Hawking, my neighbor in Cambridge, he just lived across the road from where I live. Unfortunately, he died, as you know, a couple of weeks back. And he said, success in creating AI would be the biggest event in human history. Unfortunately, it might also be the last unless we learn how to avoid the risks. And Elon Musk, who is the new Steve Jobs in Silicon Valley, and who we've just also elected to the Royal Society as a full member, because he's actually a South African, not American, I'm pleased to tell you. He said, hope we were not just the biological bootloader for digital superintelligence. Unfortunately, that is increasingly probable. So great opinion leaders in this world do feel that this is a big problem. This is something that we need to think about. And this is something we all need to think about together. And I hope you will help with that. This is Demis Hassabis of DeepMind, also a Cambridge guy. And there's this famous move of 37 in game 2, which all the Go people say was sort of the first time they felt a computer was intuitive, was intelligent. And it won the game. It was a game on, how many people play Go here? Any Go players? So you didn't waste all your time playing Go as I did when I was a physicist. It's a very complex game. It's much harder than chess. It is played on a 19 by 19 grid. And this particular move was played on column 5, which is an unusual move. It was so unusual in the early parts of the game. It was so unusual that Lee Sedol, the strongest Go player in the world, got up and walked around for 15 minutes because he couldn't make up his mind on whether this was a bug in the program and it was just an incredibly stupid move, or whether it was brilliant. And it turned out to be brilliant and won the game. Now, to our great relief as humans, Lee Sedol then played move 78 in game 4, which was equally brilliant, played by a human, and he won that game. Unfortunately, it was the only one. He won out of 5, and that's why AlphaGo won the World Championship. Now, these disruptions, like with the ARM business model, because ARM is a licensing company, that's how we now outsell Intel 20 to 1, and even in dollar terms, the ARM processors in the world are now significantly worth more in dollar terms per year than the Intel revenue. But what I just want to finish up on is not bragging about all these details, which is pretty impressive. You know, every one of I can't stop slailing about it. So every person on Earth has more than 10 arms now. Now you might ask, well, where are my 10 arms? And the answer is in your smartphone, because it's not just the application processor that's an ARM. It's the processor in the Bluetooth device, one in the Wi-Fi system, one in the USB. So there are more than 10 arms in every processor. But the effect on the car industry will be the most dramatic, because you get a change in the business model from buying a car in the showroom because of the power consumption, the horsepower, the looks. We've got wonderful BMW cars out there. And all these criteria and the wonderful motor that you see out there are irrelevant when it comes, and you don't spend 20,000, 50,000 euros on the car. You spend $10 on Uber. And do you care what car it is? No. What do you care about? Whether the car turns up quickly, what it costs, and whether it's safe. So these are very different criteria from these. And the power then shifts from the manufacturers to the service providers like 5AI, this startup that we have. And the biggest opportunity is actually in healthcare and the combination of healthcare. And this is where we're heading. We're coming to the end of evolution. You know, we started off with Aristotle here thinking about this. Then came Bayes with his famous probability formula, and then Alan Turing, who was also a member of my college, King's College, and now we've got these artificial intelligences. So in conclusion, humanity has a new partner, and they're intelligent machines, and we've got to accept that. And the key problem is going to be how we co-involve with them. I'm not a dystopian person. I don't think this is going to be a disaster. I don't believe in utopia either. I believe that we've got to co-involve and be balanced about this and think about human goals also for AI. Thank you very much.
Thank you very much. Right. Thank you. Thank you very much for that. Is this on? Yes, this is on. Thank you very much for that. It was fascinating and put a lot of facts around what is becoming a sometime emotional discussion around artificial intelligence, self-driving cars, and so on. Trying to sum up the numerous questions we have in the app, a lot of them are focusing around the area of establishing AI standards, looking at ethical frameworks. How can we arrive at an agreed-upon set of ethical and decision-making standards for things like preventing AI from taking over, or how self-driving cars decide whom to kill?
Yes, that's a question that often comes up. The reason why I'm wearing my badge here, this is a UN badge of the 17 Sustainable Development Goals. So, because goals are so important, having a global agreement on what these goals should be seems to be, to me, one of the most important ones. So setting standards, thinking about how we do this on a global basis, because this is not a national problem, this is a global problem, I think is the most important. This thing about deciding who a car should kill, it's called the trolley problem because it originally was defined as a railway carriage or a train, going rogue, and then somebody had to turn a point on whether it kills the children or the old people. It's a bit of an artificial question because this, of course, is a problem that we face all the time. But how often in your life have you faced the decision that you have to kill some babies or kill an old person and think about, well, the babies have another 70 years to live, the old guy is maybe in his 80s, he only has got another 5 years, so I think I better kill the old guy. This is just, it just doesn't happen. So it's actually not an important question, and I think we'll just have to have some, simple rule. But that's not where the real
Mercedes has designed its autonomous steering systems to prioritize the life of its passenger, the person who's paid for the car.
Yes.
So that's an example of a more realistic scenario.
Yes.
And it's also an example of a corporation making a decision for us that's non-transparent, right? And my hope is that with the UN or whomever, that society actually has to come to some ethical position that's then defensible in software.
Yes, and the ethical decision I think that most of us would buy into is that either all the lives are worth exactly the same, or, and there's some sympathy, especially now with this Brexit vote in the UK, that you give more weight to the young people than the old people. The young people, there's a big movement in the UK now, about 2.5 million students are now allowed to vote that weren't allowed to vote in Brexit. And they say, you are determining my future. Give me a vote before you actually go over the cliff. So I hope that they will vote again.
On that note, thank you very much. Thanks again.